Hello. So today we are going to finish up chapter 8 on rational numbers. And next week we'll kind of we'll have a chance to get a glimpse into the real numbers. So that's chapter 13. So we're going to jump from 8 to 13. And we won't even get to finish chapter 13, but a couple important points. I want you to get at least a little taste of what proofs in continuous realm or mathematics is going to look like. In fact, we'll get a sneak preview of it today as well. Anyways, let's get to the rational density theorem. That's the main topic for this video. Okay. All right, so I know density has a particular meaning in science, but in mathematics, when you say a set is dense in another set, so in this context, we're going to say rational numbers are dense in real numbers, and basically what it means is that if you have any element in the bigger set in real numbers, then you could always approximate that element as close as you like using the smaller set. So in this case, rational numbers. So given any real number, you can always find a rational number as close as you like to that number. That's what it means. Okay, so this is actually a really useful theorem because it gives us attraction into the real number. So real number is uncountable. So there's too many of them to use the notion of induction or so if you could use rational number as a clutch, right? So, okay, I can't use induction, but maybe if you can approximate it close enough with a rational number, and rational number is countable, then you could use induction maybe in a certain sense. So you can still use the tools that we use for rational numbers to say something about real numbers. So that's what the density is going to give us. It's a way to get around the fact that real number is difficult to work with. Okay, but before we get to the rational density theorem, we actually have to prove what seems super obvious, but it's actually, we haven't proved it yet. So we need a proof, and that's for what's called the Archimedium property. So let's look at that one. So this says that for any real number x, there exists a natural number n such that x is less than n, right? So this might seem completely obvious that there's always a natural number bigger than any real number, but it doesn't come from any axioms we've discussed or any other theorem that we proved in the class. So this needs a proof, and if you're like pushed it, like come up with a way to prove it, like you might struggle a little bit. Like you might just say, come on, it's obvious. But it requires a particular axiom that we haven't used quite yet. So let's jump right in. So we'll prove this by contradiction, right? So suppose there's some real number x such that x is larger or equal to any natural number that you could think of. So that means the natural numbers are bounded. So there exists least upper bound, y. So here we're using a new axiom. So remember, real numbers are complete ordered field, right? So we've used the fact that real numbers are a field. We've used the fact that they're ordered, but we haven't used the completeness bit. And when we were discussing about that in chapter 1, I kind of brushed it away and say, well, you might need it to get to irrational numbers like square root of 2 or something, or limits in general. And that's exactly what we need it for. So the least upper bound axiom says that if you have a set that is bounded, then there is the smallest of those upper bounds. So if natural number could be bounded by some x, then there exists smallest upper bound, y. So that means that anything above y is an upper bound of n. Conversely, any number below y, because it's the least upper bound, any number below y is not an upper bound for natural numbers. Okay, so suppose there is some least upper bound y. Then in the interval from y to y minus 1/2, there is a number in the natural number set. And let's call that element m. This has to exist because if this did not exist, then y minus 1/2 is a smaller upper bound for natural numbers. So there has to be a natural number in the interval. So we're just going to call that m. Okay, so that's equivalent to saying y minus 1/2 is less than m. If you add 1/2 to both, if you add 1 to both sides, we have y plus 1/2 is less than m plus 1. But remember, if you have a natural number plus 1 is still a natural number. So m plus 1 is a natural number that happens to be bigger than y plus 1/2. In particular, it's bigger than y. So that's the contradiction. Y is not an upper bound of natural numbers. So that's the proof. So now we have what's called Archimedium property. It's a natural number bigger than any x. Okay. All right. Let's now prove the rational density theorem. Okay. So here's the precise statement of rational density theorem. If you have any two distinct real numbers, let's call x the smaller one and y the larger one, then there's a rational number strictly between them, p, between the two numbers x and y. So there's a rational number between any two real numbers. So let's see how we use this Archimedium property to prove this. Okay, so since we have x is less than y, that's another way to say y minus x is a positive number. And this might seem awkward, but being able to find large natural number is actually equivalent to being able to find arbitrary small 1 over n. So if you use Archimedium property, you could say something like this. So y minus x might be a really small number, and which means 1 over that small number is very large. But you could always find the natural numbers larger than that. And the reason why you might try to use Archimedium property this way is to show that, well, if you rearrange this expression, you could get this, or you might say y minus x is greater than 1 over n. So you can find 1 over n, which is small. And n is going to be the denominator in this rational density theorem. So that's what's coming up. Okay, so we found n. Now we have to find the numerator for the rational number. We're going to use Archimedium property a couple more times. So let's say nx is a number. So if we use Archimedean property, we can find M1 that's greater than NX. And we can also find M2 that's greater than negative NX. Right? So I just want to pinch the NX from both sides of the equation with two natural numbers. So that's another way to say negative M2 is less than NX, which is less than M1. Notice in this expression, if I divide all three sides by n, we'll get the real number x that is pinched between two rational numbers, a negative m2 over n and m1 over n. But that's not what we want to prove, right? It's not that we want the real number to be between two rational numbers. We want to find a rational number between the two numbers x and y. So we'll have to do a little bit more work here. Okay, so if these two are integers, there's going to be, as you go from M2 and counting one by one towards M1, at some point you're gonna cross this number NX, right? So there's an integer M such that NX is between M minus 1 and M. So M minus 1 is the last one that is less than or equal to NX. And then if you add 1, you definitely get bigger than NX. So there's going to be a point where that happens because NX is trapped between these two. It will happen somewhere along the way. And then from here, we're going to do some tricky combination of inequalities. So we have NX here, which is less than M. So that's what I wrote here. And M, so if you look at this expression right here, and bring the minus 1 over to the right-hand side, we have M is less than or equal to 1 plus NX. So that's what I have here. And also from here, I'm going to use this inequality right here. So we have n times y minus x is greater than 1. That's the same thing as saying ny minus nx is greater than 1. It's the same as saying ny is greater than 1 plus nx. Okay. So this inequality right here is right here. So 1 plus nx is less than n times y. So what do we have? We have nx is less than m, which is less than ny. If you divide all three sides by n, then we'll get x is less than m over n, which is less than y. So we found a rational number m divided by n that's strictly between x and y. So you might, when you look at this proof, it looks like a weird juggling of inequality, and it basically is. But basically, what it's doing is that we have a real number line, and we have x and y. X is smaller than y. So what we're going to do is we're going to find a rational number, and what we're going to do is we're going to cut up the real numbers into small enough segments so we find an n in the denominator that's small enough so that you'll get a notch strictly between x and y. And then we'll find an m that fits in between. So once you break down into notches, you just pick the right numerator so it's stuck in between x and y. And to do that, you need notch sizes to be small enough than the interval between x and y. And that's why this thing came. For this argument, this heuristic to make sense, you might need to watch this video again. But that proves that rational numbers are pretty much everywhere in real numbers. And if you have that, it's actually not too much more effort to get irrational density theorem. So if you take x and y, real numbers, where x is less than y, then there's a z, which is an irrational, that's in between x and y. Turns out that, I mean, this seems like just as an important theorem, but irrational density is actually not as useful because irrational numbers is not countable, and it doesn't give us too much more tools just by knowing this theorem. But it's good to know. So let's prove that really quickly. Okay, so we're gonna use the rational density theorem. So take a non-zero rational number p between x over root 2 and y over root 2. I say non-zero because I want to be able to divide by it. But if you have to pick 0, then you're kind of already done, right? 0 is, well, never mind. Let's pick a non-zero rational number. And then since this is equivalent to saying x over root 2 is less than p, which is a rational number, which is less than y over root 2. So if you multiply all three sides by root 2, that's equivalent to saying root 2 times p is between x and y. And this is going to be our candidate for that irrational number. So my claim is that if you take a rational number and multiply by square root of 2, you'll get an irrational number again. Let me convince you how. If it happened to be rational, then remember rational numbers are closed by multiplication and division, right? It's a field. So you could divide by a rational number p to get square root of 2. And square root of 2 should be rational because it's rational number divided by a rational number. But we've actually already proved that it's not rational. So that means that square root of 2 times any rational number is irrational number. Okay, so our square root of 2 times p is our irrational number. It's between x and y, and we're just gonna say z is that guy. Okay. So this, like, if you think about this a little bit, like it's easy to kind of convince you yourself that rational and irrational numbers are comparable. Like between any two rational number, there is an irrational number, and between any two irrational numbers, there's a rational number. So you might convince yourself that there's just as many rational numbers as there are irrational numbers. But it turns out that that's totally false. There are actually way, way more irrational numbers than rational numbers. So because real numbers are uncountable and rational numbers are countable, you can't take a union of two countable sets to get uncountable set. We've actually done an argument like that before. So irrational numbers are uncountable. In fact, we don't have enough real analysis to prove this yet, but if you took a soup of all real numbers, or maybe interval from 0 to 1, and you randomly scoop up a number in that interval, then with probability 1, you're going to get irrational numbers because they're so much more abundant than rational numbers. So, right, I just, density and the size of the set is not, it's not on equal footing, I guess. I guess that's what I wanted to say. Anyways, that's it for this video. I hope you enjoy that. And I'll see you soon.